In this series of videos, we're going to be learning about a few scientific experiments that helped us determine the modern understanding of how an atom and its electrons are organized. Now, in order to understand where this discovery came from, we need to go all the way back to the beginning before we even knew what the structure of an atom was. And this goes all the way back to the discovery made by a French physicist, Henri Becquerel, who studied certain elements, including uranium, and found that they emitted forms of energy that hadn't previously been categorized. Now, this discovery was picked up on by a pair of French physicists and chemists, Marie and Pierre Curie, and yes, this is the same Marie Curie who is the first female scientist to win both the Nobel Prize in physics and in chemistry, and she did so because of her discoveries involving elements such as polonium and radium. We, of course, today recognize that polonium and radium are both examples of radioisotopes, and this discovery of theirs was nuclear radioactivity, which is that certain unstable nuclei that have very, very large amounts of positive charge that makes their nuclei unstable, emit certain forms of energy, and this is what we call nuclear radiation, which exists in three forms. The first of which is what we call alpha radiation, in which a particle equivalent to the nucleus of a helium atom, that being an atomic mass of 4, and a charge of positive 2, which again is equivalent to a helium atom without any electrons. And this is what we call alpha radiation. Beta radiation, on the other hand, has no mass and a charge of -1, which means that a beta particle is functionally equivalent to the release of an electron, whereas gamma radiation, most famous for being very deadly and cancer-causing in high enough doses, is a pure form of energy in that it lacks both any visible mass, or observable mass rather, and any observable charge. Now, even though this discovery doesn't help us in terms of electrons, it was integral to future experiments that were done that helped us determine how electrons fit in to the structure of an atom. And the first of these experiments was conducted by an English physical chemist by the name of J.J. Thomson, also known as the scientist who discovered the role of electrons. Now, what J.J. Thomson wanted to show is that an atom actually has a combination of positive and negative charges. The problem with proving this is that most atoms exist in their neutral form. So the element that he was working with was hydrogen gas, simply because of its abundance. Hydrogen is by far the most common element in the universe. And what J.J. Thomson was able to do is, if he trapped hydrogen gas and put it under a very high temperature and pressure, and then passed electrical current through it, he created a form of the element previously uncategorized and subsequently named this plasma. So plasma is better known as what we call ionized gas, because when we take a gas such as hydrogen, or really any gas, and subject it to high temperature and pressure, and then pass an electrical current through it, we actually get something that looks like lightning here, and indeed lightning is a form of plasma that exists in the atmosphere when the gas in the atmosphere is heated and put under tremendous amounts of pressure with an electrical current flowing through it. Now, how did J.J. Thomson use this to discover charged particles? Well, what he did is he took ionized hydrogen and passed it by an electromagnet here. Now, if he were to do this with neutral hydrogen would not respond to a strong positive or a strong negative charge in either way because of the fact that it is neutral, but since plasma is ionized, this is not what happened. So what J.J. Thomson observed is that plasma can actually be focused into a visible beam of light similar to a laser, and basically this is an electron beam, which is actually the foundation behind how early TVs and other projection screens worked. And what he observed is that this beam of electrons that was produced from ionized hydrogen gas would actually bend as he moved an electromagnet close to it, because negative charge does not want to be near other negative charge. So increasing the strength of the negative charge on an electromagnet actually caused the electron beam to bend away from it like this. And this proved to J.J. Thomson that atoms were not in fact neutral, that atoms actually consisted of equal quantities of positive and negative particles. And from there, he came up with the term electrons to describe the negative particles. Now, the incomplete feature that J.J. Thomson didn't understand, because he didn't have enough information from this experiment, is he didn't actually know where the positive and negative particles that make up an atom were and how they were organized. And J.J. Thomson, using what we now know as common sense from the law of attraction, assumed that because positive and negative charges attract to each other, we would find the positive particles, the protons, and the negative particles, electrons, together inside of a structure that became known as the nucleus. So this model here was the original model of how an atom was structured, although, as we'll see in the next video, another scientist, one of J.J. Thomson's successors, set out to prove whether Thomson was right, and ended up discovering that this structure, however well conceived, was actually inaccurate. And as a fun fact, this model was originally referred to as the blueberry muffin model, where the nucleus was regarded as the dough part of the muffin, with the electrons embedded within the positive charge being individual blueberries that were found within the muffin. In the next video, we're going to look at that successor experiment, the experiment of New Zealand physicist Ernest Rutherford, and how he demonstrated that J.J. Thomson's model, however well-intentioned, was ultimately an inaccurate representation about how electrons and protons are structured in the nucleus.